welcome to the course Advanced Reaction Engineering. So, today we will discuss about non-ideal flow, that is the segregation model. So, already we have discussed many reactors. So, batch reactor, plaque flow reactor and CSTR, and there are some residence time distribution studies that we have discussed. So, now with the help of RTD, means residence time distribution functions for any reactors, how we can predict the conversions and exit concentrations. So, in the segregations model, so RTD that we have discussed, or RTD we have measured for a particular reactor. So, that is not the complete description of the structure for a particular reactor or the systems to find the conversions or exit concentrations. So, therefore, suppose if RTD is the unique for a particular reactors, but the reactor systems or reactors is not unique for that particular RTD. So, for a particular reactors, whatever we are design, that particular reactors we have to measure a particular RTD, and based on that we can find out the concentration and exit concentrations conversions that we can find out. So, in addition to the means RTD or residence time distribution function, so flow patterns of that fluid that is feeding from the reactors. So, that quality of mixings means that we should know, or the degree of segregations. So, therefore, with the RTD models or for any reactors, once we know the RTD or residence time distribution functions, with that we have to develop some models and kinetic data that we need. So, once we know, then exit concentrations and exit conversions that we can find out for that particular reactor. So, there are so many models are available for the residence time distribution functions to predict the concentration and exit conversions for that particular system. So, 0 adjustable parameter models, that is called segregation models, models, 1 adjustable parameter model, that is the Tang and series model, dispersion models, and 2 adjustable parameter models, that is the real reactors models as combinations of ideal reactors. So, therefore, first we will discuss about the segregations model. So, in the segregations models, it actually tell us about the mixings of the materials or that reactant molecules that is feeding in the reactors. So, whether it is proper or not. So, or with the help of this we can find out the or predict the conversions or concentrations. So, for a first order, let us say for a first order reactions, if we know the design equations for the batch reactors. So, let us say first order reactions we want to conduct in a batch reactor. So, and then the design equations we can write this way: minus dNA by dt equals to minus RE into V, and Na equals to Na0 into 1 minus x, and dx by dt equals to k into 1 minus x. So, here if we substitute this in here, and then if you simplify, then we can get it this. Okay. Or you can write this for a first order reactions. Here red we have considered first order, and considering that we can get it, means changes of the conversions as a function of temperatures. So, here kinetic parameter, that is the rate constant for that particular reactions we should know, and then we can do it. Okay. So, RTD and mixings both we know. So, means degree of mixings when that molecules passing through the reactor. So, molecules each molecules should pass through the reactors, and that whenever it is passing through that reactor. So, it may, if let us say 2 different molecules passing through the reactor. So, then if 2 molecules come in contact and properly mixed come in contact at particular temperature, then reactions may possibility. If the mixings is not proper and 2 molecules does not come in contact each other, so then there the means reactions or conversions that would be different from expected. So, here the mixings that we can say it is microfluid or macrofluid mixing. So, 2 different way, means molecular level we can think here. So, when this is the entrance of a or feed inlet points of that particular reactor, this is outlet points. So, here, so when molecules is entering from here to leaving this way. So, here you can see that molecules in that in the form of sphericals means we are considering a small bubbles. So, where inside of that molecules which presents, here also molecules which presents, but here the molecules in these globules and in these globules are different. So, but in these globules, so what are the molecules are present? they are mixing each others and they are having the same residence time, and this particular globules having molecules, all molecules spending same or equal times when they are passing through the reactor. But these two means molecule, these globules and these globules residence times and mixings are different. So, individual globules we can consider as unique molecules that we can consider. So, if it is does not mix, these globules does not mix with these globules. So, then individual globules, what are the molecules present, they have unique residence times and unique space times for that particular reactors, and here the mixing is called macrofluid mixing. Okay. And when the globules enter in the second cases, here globules enters or molecules enters, after that when it is mixing. So, mixing the molecules is very small, means all molecules mixing together, here mixing is called microfluidic mixing. So, here mixing is proper. So, all molecules also spending here, and here each globules are free to move everywhere inside of these reactors. Okay. So, here without specifying high molecules different edges encounter one another, and here molecules are different edges encounter one another, but here we are not specifying. So, in this case complete segregations molecules in this case is possible. In this case, since each globule inside of that globules, what are the molecules present, that is coming out reacting inside of the reactors, and that way it is following that pathway, but other molecules or globules following different pathway. Okay. So, therefore, here complete segregation is there in this particular way, and in this way complete mixing is there. So, molecules of different edges are group completely mixed at molecular level. So, these are the basic difference in these cases. I means macrofluid or microfluidic mixings when reactors are there. Okay. So, here we consider that molecules in this particular segregations models. So, we are considering this type of CSTR reactor, and here molecules globules of a given edge do not mixed with each others, or macrofluidic mixing is there. So, individual globules, what are the molecules are present inside of that globules, they may be converted inside of theirs, and then it is passing through these reactors and coming out. So, similarly other globules also following the similar way. So, it is macrofluidic mixing is there. Microfluid in segregation models has mixings at least possible points. So, mixings if it is there at the outside or just whenever it is coming out, then mixing is possible, but individual globules they does not interact with each others and does not mix inside of the reactors. Okay. So, that way it individual globules coming out from the reactors. Okay. So, here if we consider a plaque flow reactors in the for the segregation model, it would be much more clear for you. So, in the segregation models we have considered a continuous flow systems of a plaque flow reactors, and in that plaque flow reactors this is the exit and this is the inlets. Here the volumetric flow rate, that is the V naught. So, for the inlet and outlet points. So, once reactant molecules passing through this reactors. So, from here we have means point out one exit, another exit, this way that reactors at different locations we are taking out the fluid molecules, and then here we are connecting, and then it is considered as a outlet or exit of the reactors, exit from the reactors. This is inlet points. So, here the residence time. So, here so when that molecules entering inside of the reactors and then it is leaving from the reactor. So, then the space times that is spent, that molecules leaving from this particular point 1 is tau 1, from point 2 it is tau 2. So, point 1 the molecules spending it has the residence time or space time that is tau 2, and at point 2 the molecules having residence times or space time that is like this. So, individual molecules having different residence times or space time, therefore, each molecule spending different time inside of the reactor to for conversions. So, therefore, overall this is the model systems for PFR reactors. Okay. And this is the E curves or whatever the concentrations will come out, and based on that if we draw the exit distribution or RTD functions for this particular systems, it would be like this. So, now so here's the means here's if we consider at this particular points at point 1. So, when molecule spending tau 1 space times, it has a conversions x 1, and at point 2 that has space time tau 2 and conversion is x 2. So, like that this is the exit point. So, here space times and corresponding conversions here from the outlets after mixing all point, here the conversions will get, that is the average conversions that will get. So, if we have to sum up x 1, x 2, x 3, x n point, and after that if we take average, so then that will get average conversions for that particular system. This is the model system. So, now so in this particular model, so the molecules moved near the entrance, it has short residence times, and the molecules that channels rapidly through the reactors, this corresponds to the means effluents. So, here I said this way it would follow the residence time distribution of space times. So, at this particular points molecules having less residence times or space times, and at this particular points molecules having longer residence times or space times that spends longer period of times. So, what are the globules or molecules individuals globules we are considering. So, let us say this is the globules, inside of that globules it contains molecules. What are the molecules, and inside of these globules we can say that it is as small, and here whatever the conversions is taking place, and individual globules we can consider as a batch reactors. Okay. Individual consider as a in the inside of the plaque flow reactors, individual globules we can consider acts as a individuals batch reactors where the molecules does not interchange with other globules. So, therefore, here the conversion inside of the reactors would be, or inside of the globules would be same anywhere, but one globules to other globules the conversion concentrations would be different. So, these globules and these globules, two different globules having different concentration, different conversions. Okay. So, now based on this is the assumptions, and based on that if we from the exit outlet we want to measure the concentrations, and if you want to find the conversions. So, then average concentration of the effluent stream or mean conversions we can get. The average conversions for all the globules, that is the exit stream that we will get. So, this. So, here's dx bar, that is the mean conversions of those globules spending between time t and t plus dt in the reactors, and then conversions achieved each globules after spending time t inside of the reactors. So, this corresponds the individual globules we have considered, and this is the x t. Okay. Here individual globules having the conversion, that is x t, individual globules we are considering a single batch reactor, and if the reaction is let us say first order reaction, and if you know the reactions rate constant for these reactions, and so then the average or these conversions individual globules we can find out, and then within that the fraction of materials leaving, so that fraction of globules that spend between t and t plus dt if you know. So, that residence time or fraction of molecules if you know, and the conversions if you know, then average conversions we can find out. This is the from the segregation model, this equation is the key equation to find the average conversions. So, now if we write the equations this way, okay, and integrates means since there are n number of globules, so many globules are there. So, if we integrate this equation, these equations, and then in the left hand sides after integration 0 to infinite we get x bars, that is the average conversions that we are getting from the exit point of the reactors, and in the right hand side. So, what are that components are present, that is the conversions from individual globules, and that is the residence time distribution function for that components, okay, or each globule. So, therefore, for overall systems conversions if you want to know, or that is the mean conversions, these equations you have to find out, and then depending upon the reactors either it is plaque flow reactors or CSTR reactors, we have to put the residence time distribution functions and then average conversions we can find out using these particular models. Similarly, the average concentrations also we can find out using these equations. That equation is similar. Here Ca bar is the average concentrations and Ca is the individual globule concentrations, and Et dt, that is the residence time distribution, Ct is the residence time distribution for that particulars. If we sum up from 0 to infinite times, so then average concentrations we can get, okay, from the segregations models. So, once we know the segregations models, so now consider a batch reactors. If we want to find out the average concentrations or average conversions, so then this is let us say reaction, first order reaction that I said. So, batch reactors design equations or minus dNA by dt equals to minus RAV, that we know, and n equals to n naught into 1 minus x, that we know. For that concentration or moles, that OH changes, finals, this is initial, this is conversions. So, if we substitute that in that equations, and after these differential equation simplifications we can get this, and after integrations of these equations we can get x t equals to 1 minus e to the power minus k into t. That is the conversions inside of a batch reactors. Let us say we have a batch reactor, here we are conducting these reactions. So, here the conversions, what would be the conversions, that equations we can write 1 minus e to the minus k into t. So, here if we know reaction rate constant and times, so then what would be the conversions for this particular batch reactors we know. So, in segregations model, each globules we consider a batch reactor. So, therefore, each globules must have conversions this, okay, or this. So, therefore, the conversions we are substituting here, considering each globules, what are the molecule spends, this is as a batch reactors, and if it is batch reactor, so then for one globules the conversion is this. So, like that a number of globules are present. So, then we can substitute here, and these equations we can simplify, and then we can get these equations. For this is the general equations to find out the average conversions for the molecule spendings and considering the segregations models. Okay. So, this is the final equations or equations we can get. Now, we have to determine the conversions by considering a ideal plaque flow reactors or ideal CSTR reactor. This is the general equations we have find out by using segregations models. So, now these models we can implement either a PFR or we can use a CSTR reactors. So, one by one we will discuss. Okay. So, first consider a plaque flow reactors implementing the segregations models in a plaque flow reactor. So, ideal plaque flow reactor residence time distribution functions is Et equals to delta t minus tau. So, that we have discussed in your previous class. So, therefore, Et we can consider this, and here we are considering reactions is the first order reactions, n equals to 1, that is the first order reactions. Okay. So, then Et equals to delta t minus tau and x t equals to 1 minus t to the power minus k t, both we are substituting in these equations. Okay. So, then we can get this, or after substitution we can get this. So, this is the now these equations, this component part if we consider, so then it would be like this. Okay. So, x bar equals to 1 minus this part, actually integration 0 to infinite e to the power minus k t delta t minus tau dt. So, that would be e to the power minus tau k. So, this is equals to or 1 minus e to the power minus d, or d equal to Namkhole Namka, that we have discussed in our previous class when we have studied the residence time or space times. On that times we have discussed what is the Damkhole number for first order reactions, d equals to tau k, or this way or either this way we can express. So, from the segregations models, the average conversions that is equals to 1 minus e to the power minus tau k for plaque flow reactor, this is for PFR reactors. So, that way means we have developed from the segregations models. So, if we do not have segregations models from the plaque flow reactors also, this type of equations also we have developed earlier. From these equations if we integrate, so this way we can get this. So, both the equations you can notice. So, from the segregation model we are getting these equations, and from the batch reactor data or considering a first order reactions. So, these conversions also we have developed. Okay. So, this way, okay, considering a first order reactions and a batch reactors. So, this equals to this. Okay. So, now these equations we can use to find, this is the model equations. Okay. After substituting E t and x t, so we can get this average conversions. Okay. Now, if we consider a plaque flow reactors. So, once we consider a plaque flow reactors and apply the segregations model. So, this is the general equations average conversions that we are getting from the exit point of the reactor is this, and residence time distribution functions for a CSTR reactors is this, and x t equals to 1 minus e to the minus k t that we have received from batch reactor data analysis. Okay. So, now these two one by one, if you substitute first x t we have to substitute here, we can get it, and then after simplifications we are substituting E t. Okay. So, then if we simplify these equations, then it would be like this. Okay. So, x bar equals to tau k by 1 plus tau k. So, that is the predicted conversions or average conversions, and from the CSTR mole balance equations also similar equations we have developed. So, both are identical. So, means by considering segregations models, the equations we are getting to find the average conversions, and by considering these reactors models for a CSTR reactor from the design equation, this type of equations are also we are getting. So, both are the equations are similar. So, from the model equations we can use these equations to find the average conversions for this particular reactor by considering the residence time distribution functions. Okay. So, now one numerical problems or examples we will discuss considering the segregations models and considering RTD distribution functions, how we can find the average conversions. Okay. Let us say this is a reactors, let us say here we are considering these reactions, and in this particular reactions rate constant that is given at 320 Kelvin is given, and here if we conduct a tracer test or RTD study or tracer test if we consider for this particular reactors. So, without conducting reactions. So, then the pulse tracer injections. So, here the tracer concentrations at different CT tracer concentrations at different times we can find out. So, this table is given. So, this is the residence time distribution functions on tracer test results is given. So, with that tracer test how we can find out the conversions if we conduct these reactions here. Okay. So, number 1 is the tracer test. So, considering this tracer test we can predict the average conversions for these reactions. Okay. Here reactions rate constant is given, we are not conducting these reactions here, only we can predict by whatever that we have the tracer test, and with the help of the tracer test we can find out the average conversions. Okay. So, by considering the segregations model. So, now in the segregations models average conversions equation is this x bar equals to 0 to infinite x t e t, these equations we know that we have developed for segregations models. Okay. So, we have tracer test experimental data. So, now what we have to find out E t residence time distribution for these reactors we have to find out. So, first we have to find out from the this is the data is given from the or collected from the tracer test experiment, then we can find out E t, we can find out x t, then x t into E t we can find out x t, this was used for to find the x t. Okay. So, here we know k and t. So, x t we know. So, now these are the components we developed or these tables we have developed. So, now step 1 means to develop these tables we need this, we need E t. Okay. Once we know E t and C t, from C t we know means first we have to find out C t, C curves, then E curves or E t. So, this E t has developed using this, and C t this point means this we have to implement here, apply here, then we can get only E t. Okay. So, how time and concentrations, the data we have from there, how we can find out ET. So, that is given by step 1 and step 2. Okay. Then xt also we can find out that rate constant for this particular reactions is given, that is k value is known. So, then at time is known, at this particular times we can put xt value we can find out, and then this we can xt into ET, we can this value we can find out from these tables we can get. So, now if we do integrate 0 to 14 minutes, so then this value after integrations that would get this. Okay. So, by using Simpson's 1/3 rules that we have discussed already, Simpson's 1/3 rules that have to implement, or other rules are available to integrate or to find out solve these integrations. So, that we have discussed in our previous class or long day back, that class we have taken. So, there we have discussed this. So, therefore, from here we can find the mean conversions for these reactions, means we have conducted only treasure test. This is the treasure test results, this is the treasure test results. So, CT T and CT, this results is treasure test results. So, with the help of treasure test and reactions rate constant, so that is the things are knowns. Using these equations, means segregations model equations, we can predict what would be the average conversions, that is 38.5, means 38.5% conversions we can get. Okay. So, if we conduct the reactions in a that particular reactors where that treasure test was conducted and this data was obtained, then if we use the segregations models, so then we can get 38.5% conversions for this reaction. So, this is the take home, means what are the things we have studied. So, first we have discuss about the different type of mixings and what are the different models are available, and based on that we have considered segregations models, and segregations models we have discussed and we have derived these equations, and then mean conversions and mean concentrations equations we have developed, and then we have applied that to in a CSTR reactors and plaque flow reactors, and that final equations we have developed, and considering that we have considered a numerical examples, or one problem was taken. So, that data are given, and there we have implemented the segregations models and used these equations to find the average conversions for that particular reactors. If we consider this reaction first order reactions, and if we know the reactions rate constants, then easily we can find out the average conversions with the help of treasure test. Thank you. So, today is up to this. Thank you.